So now that we know the SI system is the choice system to use, let's look at how the primary units of time, length, and mass are defined in the SI system. Time, for example, before the 1960s, the standard of time in the SI system, which is 1 second, has to do with what's called mean solar day. Okay, so basically we take what's called a mean solar day and divide this into 24 pieces. That gives you 1 hour, and each hour is divided into 60 minutes, and each minute is divided into 60 seconds. But of course, that is not all very precise because it depends on how the Earth moves around the Sun, that sort of thing, which is fairly constant, but not quite that constant. Then, in 1967, a new definition came upon for seconds, and that has to do with the famous atomic clock. What they did was they chose a particular atom called cesium-133. Okay. This particular atom is used as what's called a reference clock. So what's a second? Well, there is a particular radiation coming from the cesium atom, and it vibrates at a very, very high frequency. Okay, many, many times a second. And so what you do is you take this vibration, okay, this particular vibration comes from a cesium atom, which will never change with time. Okay, it's very, very much a constant. And you say, okay, this vibration is very, very fast, so the period of this vibration is extremely short. It's a very, very small fraction of a second. What fraction? Okay, 9,192,631. Well, I lost track actually. It's 9,192,631,770 of a second. Okay, actually that's in your textbook. You don't have to remember these particular numbers, but just remember the definition of a second is now tied to the vibration of a certain spectral line from this particular atom called cesium-133. And this is a highly accurate definition, will never change with time. It's very, very constant. And the measurement of time using atomic clock is the most precise measurement human beings have learned to use. So it's highly, highly accurate. Now, what about length? What about length? Well, the measurement, the standard of length in the SI system, historically, what the French did to establish the unit system was they took a certain metal bar. Okay, they took a certain metal bar, and they precisely cut this metal bar at both ends, and they say, all right, the distance between this end and that end of the bar is called a meter. And this metal bar still exists today. It is housed behind a double glass jar in the International Bureau of Standards outside Paris. And that definition, which is, the 1 meter distance between this end of the bar and that of the bar, was kept until the 1960s. Okay? But you think about it, this measurement, this particular definition, is not all that precise, right? Because, first of all, you can say the length of the bar can actually change with temperature and pressure, right? Okay, then you say, let's fix the temperature and fix the pressure. Even so, do you really think that the two ends of the bar are precisely sharp so that the distance between one end and the other end is well defined? Well, not under a microscope. Isn't that so? If you take a powerful microscope, you find, this edge, that edge, it's not really flat and smooth. Rather, it's, it's not well defined at all, right? It's rugged, right? If you look at the situation from a microscope. So you see that that definition is not very precise at all. Plus, there is one more problem, and that is, it is not easily duplicatable. Okay, now what if, for whatever weird reason, God forbid, something happened to that bar, so that the world wakes up the next day and finds, gee, that bar is gone, okay? Cannot find it anymore. Does that mean we're going to lose the scientific definition 1 meter permanently? Well, that would be a disaster, right? Because then everybody can claim, okay, now I can define 1 meter, now you can define meter, and then it will be a chaos, right? If you do not have a standard, universal accepted definition of a meter, for length, that of course will be in trouble. So let us redefine 1 meter such that, first of all, it is scientifically accurate, and secondly, it is easily reproducible. Okay, it does not depend on one particular bar or one particular piece of substance that's well kept. No matter how well kept it is, still dangerous. So, believe it or not, the length unit, 1 meter, the most recent scientific definition was as close as the year 1983. There is an international committee whose sole job is to refine the definition of these basic units. Okay, so in 1983, in October 1983, the definition of 1 meter was rewritten, and this time it is tied to a universal constant of nature, the so-called speed of light in vacuum. As you will learn from Einstein's theory of special relativity, the speed of light in vacuum is a universal constant. It's the same here, it's the same everywhere in the universe. It never ever changes. Okay. Now, the speed of light, that's a constant, and light travels roughly about 300 million meters per second. Roughly, it's a little bit lower than that. Okay, so roughly speaking, what's a second? Roughly speaking, what's a meter? A meter is a distance traveled by light in a very, very small fraction of a second, right? Because see, in every second it moves about 300 million meters, and therefore 1 meter is the distance traveled by light in roughly 1/300 millionth of a second. Okay, of course, you don't want to use 300 million even, because that will conflict with the original definition of a meter somewhat. So you want to be more precise, right? So the more precise number defined in 1983 is that a meter is the distance traveled by light in vacuum during not exactly 1/300 millionth of a second, but rather 1/299,792,458 of a second. Okay, so it is tied to the speed of light in vacuum, which is a constant. Why is this a better definition? Well, first of all, it is tied to a universal constant, which is the speed of light in vacuum. Okay, so you never have a problem of reproduction. You can always recover that definition. It is not tied to a particular metal bar or anything like that, or anything on this planet for that matter. Okay, it's a universal standard. And secondly, of course, in order to measure 1 meter, you must be able to measure a very, very tiny fraction of a second, right? In this case, like 1/300 millionth of a second. But the measurement of time, as I said, is the most precise measurement human beings can ever take with today's technology. So this is not only universal, but also very practical, because we know how to measure time very precisely. Okay, so this gives us the best definition of 1 meter. Now, what about mass? Well, originally, the French, during the establishment of the SI system, they made a specific platinum-iridium alloy cylinder. Okay, and they say, all right, the mass of this cylinder is defined at 1 kilogram. And this cylinder today is still kept at the International Bureau of Weights and Measures outside Paris. And believe it or not, this is still the definition of a kilogram currently in the SI system. But of course, you say, well, that will be a problem, right? And this problem, that problem. But we're not going to worry too much about it. First of all, this cylinder has been duplicated throughout the world, and secondly, we have some sort of auxiliary unit, auxiliary measurement for mass. We can, for example, take 12 grams. Okay, we take a large number of carbon-12 atoms, very common carbon-12, the most common type of carbon, and we take roughly 6.022 times 10 to the 23. We take that many carbon atoms, put them all together. We call the mass of that many carbon-12 atoms 12 grams exact. So that gives us some idea how to find a gram, right? Once we know how to find a gram, of course, we know how to find a kilogram. So even though the primary definition of 1 kilogram is still tied to that particular cylinder, there are other ways to recover that definition if there's anything that can happen to it. Okay, so you see the definition of these basic units, like what is a second, what is a meter, and what is a kilogram. We don't really think about it, right? Usually, it doesn't mean these are easy to obtain. Okay, the definition has to be very has to be very precise. Okay, it also has to be easily duplicatable, and it's not always easy to achieve these things. And that's why scientists spend decades and actually centuries trying to refine these definitions. Okay, but we do have precise definitions for these base units. Of course, based on that, we can also have derived units. What's a derived unit? Let me give you an example. Okay, primary units, that of in mechanics, we have that of length, time, and mass. What about the derived unit? Well, for example, speed. It is measured in meters per second. Right? Say you run at 3 meters per second, so every second you move forward by 3 meters. The unit, so your speed is 3 meters per second. That unit of speed is the unit of length divided by unit of time. So it's a combination of primary units. That's called a derived unit. Okay, so with 3 primary units, meters, kilograms, and seconds, we can get a whole bunch of derived units, that of speeds, acceleration, force, momentum, all of these things that we can find later. So we don't just have 3 physical quantities in mechanics, of course, with many quantities, but they can be all taken care of with derived units. Again, there are only 3 primary units in mechanics: meters, kilograms, and seconds, in SI system, that is. All right, let us do a little review of what's called the scientific notation and orders of magnitude. It is clear that in physics, we are often dealing with a very wide range of quantities in terms of magnitude. Sometimes we deal with very large quantities, sometimes very small quantities. And you learned before that when you have to deal with very large or very small quantities, it is a good idea to write that quantity in what's called scientific notation. An example: the radius of the Earth is about 4,000 miles. Okay. Now, to be more precise, if you want to write it in meters, it's about 6.37 times 10 to the 6 meters. That is an example of scientific notation. What is the advantage of scientific notation? Well, if you don't do that, you have to write 637,000 meters. Why is this a better notation? Well, a couple of things. First of all, you have to count how many zeros you have, right? So, okay, 1, 2, 3, 4, 4 zeros, and then you have to, okay. So this is you say, okay, this is 6,370,000 meters. So here you don't have to count. Immediately you know it's 10 to the 6. Okay, it's a million, right? It's roughly 6 million, 6.3 million. So it's immediately you know how big it is. Okay, in other words, the order of magnitude is 10 to the 6 meters. Immediately you know. This is from the scientific notation. You know immediately how big, how small it is. You don't have to count all these zeros. Okay, that's not a very large number. If you look at, for example, how many meters light can travel in a whole year, that's called a light year, and you have to deal with a lot more zeros, right? It's difficult to count, so that's why we use scientific notation. Another advantage of scientific notation is you can immediately see how accurate the measurement is. For example, if you write it this way, you never know whether this zero is accurate, that zero is accurate, whatever. Is it really? Do you really know the radius down to a meter or 10 meters? It doesn't make any sense, right? It's not possible to write, measure the length of the Earth, the radius of the Earth that accurately. But with this notation, it's clear that you know these three significant figures, 6.37. You don't know what the next one is. So it's your accuracy is down to 0.01 times 10 to the 6 meters. It's about 10,000 meters or 10 kilometers. That makes sense. Okay, so you will know how big it is, and you will know the accuracy immediately by using the scientific notation. Okay, and let's look at a couple examples. Okay, how we might estimate the orders of magnitude. Well, one of the most interesting cases is to find the number of seconds in a year. Now, this is not hard to do, okay? We can easily do that. First of all, how many seconds are there in an hour? So that's 60 minutes times 60 seconds per minute, so that's 3,600 seconds per hour. Then times 24 hours, right? 24 hours. That will give you the number of seconds in a day, and you multiply 3,624, you get, trust me, 86,400 seconds per day. Okay, I mean you can do that yourself, but that's the number that you'll be getting. Now, how many seconds do we have in a year? Well, no problem. You take that number, multiply by the number of days in a year, right? 364.25, whatever, or 365, you want to be just roughly. And then you get okay, 364.25 days in a year. That will give you the number of seconds in a year, and to the first 3 sig figures, if you work this out to the first 3 sig figures, that will give you 3.15 times 10 to the 7 seconds per year. That is an interesting number. It's not hard to calculate, but it's a number that has a lot of interesting uses. You may not remember this number easily because it doesn't really resemble anything. It's not something that you have a particular attachment. But if you really look at it, 3.15, okay, it is very close to a number that everybody knows by heart. What do you think that is? Very close? Yeah, how about pi? Okay, what is pi equal to? 3.14, right? To the first 3 sig figures. Now, this is not exactly pi. It's a little bit more than that, but don't worry about it. It's close enough. Now, so we say 1 year is roughly pi times 10 to the 7 seconds. Okay. Why do we replace it by pi? Because we know pi very well. Okay, so roughly speaking, it's 31.5 million seconds in a year. Okay, this is an interesting observation. With that, we can easily estimate, for example, how many heartbeats does a person go through in a lifetime, roughly speaking. Well, let's see. You have, let's say, a person lives to be 100 years old. Okay, that's not too bad, right? That's not too bad. So you basically, in each year, how many heartbeats are there? Well, let's see. For simplicity, let's estimate the heart rate to be 60. Okay, so what that means, 1 beat per second. That's not a bad approximation for most people. And then you say, all right, there are this many seconds in a year, so that roughly speaking, you have pi times 10 to the 7 heartbeats per year. Multiply this by 100 years. So roughly speaking, you will have pi times 10 to the 9 heartbeats. Okay, so roughly speaking, if you, let's say, okay, it's not quite 100 years, maybe 90 years, whatever. You're looking at a total heartbeat of about 3 times 10 to the 9. In other words, 3 billion heartbeats, okay, in a lifetime. Now that's a lot, by the way. And if you can make $1 with every heartbeat, then you'll be $3 billion rich after nearly 100 years. So that's an interesting number to think about. Okay, so you also can estimate roughly how many seconds does an average person live. Of course, you say it's kind of scary to measure your time in seconds, right? But don't worry, it's a lot of seconds. Okay, so roughly speaking, 3 billion seconds. That won't be bad at all. This is way over 80 years old. Okay, so 3 billion seconds is not bad at all. So that's an interesting number, and there is a little story associated with that conversion here. Once upon a time, there was an international scientific meeting. Okay, and during one session of the meeting, the chairman, was in charge of allocating hours or minutes to each scientist who wished to talk about their scientific discoveries. So before each person starts to talk, the chairman will ask him, "How long do you want to speak?" Right? Normally they would say, "Okay, I want I want to use 30 minutes or 1 hour, whatever. Now, then he asked this particular scientist, and the scientist was interesting. He said, okay, I need 1 microcentury. Gee, what is a microcentury, you wonder? That sounds like a very long time, right? Because you use century instead of seconds, okay? But really, you think about it, okay? The German was very clever. He thought about it for a few seconds and said, okay, go ahead. And then the scientist spoke for how long? For about 50 minutes. So now, tell me, what is a microcentury? Don't use your calculator, okay? What is a microcentury? It's not hard to do it at all because you know how long a year is in terms of seconds. Okay, a century is 10 to the 2 years, right? It's 100 years, right? A micro, what's a micro? A micro is 10 to the negative 6, isn't it? So what's a microcentury in terms of years? It's 10 to the 2 times 10 to the negative 6. So how much is that? That's 10 to the negative 4 years, right? That's a microcentury, right? Each year, you have pi times 10 to the 7 seconds. Okay, so how many seconds are there in a microcentury? You take this number and you multiply this by 10 to the negative 4. In other words, you get about 10 pi times 10 to the 3 seconds. Okay, let's say pi is about equal to 3. So basically that's 3,000 seconds. Okay, just 3,000 seconds. 3,000 seconds divided by 60 seconds per minute. How many minutes would that be? That would be 50 minutes, you see? Okay, actually it's a little bit more than that because pi is more than 3. So if you want to be picky, you get about 52 minutes for a microcentury, but 50 is a good enough approximation. So it is obvious that the chairman must already knew this conversion, otherwise he couldn't do it that fast, right? But with that conversion, you easily know what a microcentury is. Okay, so that's an interesting little story to tell you so that you will have a better memory of this interesting conversion.